Hello, welcome. My name is Maloy De. I did my PhD in Statistics from Calcutta University in 2007. Today, I'll be giving a popular talk on my thesis. The title of my thesis goes as Some Contributions to Two Estimation Problems, Estimation of Common Mean and Estimation of Size of a Finite Population. Part 1 is Estimation of Common Mean and part 2 is estimation of size of a finite population. Let me start with part 1. So what is estimation of common mean? Suppose we are monitoring gasoline quality based on read vapor pressure using two methods. One is a cheap and quick method yielding crude measure obtained on site. Say we take 10 samples by this method, and then an expensive laboratory analysis yielding a measure of presumably higher precision, which is costly also and time taking. And suppose we take 10 samples using second method. Now under normality assumption, sample mean is the best estimator for each method, uniformly minimum variance unbiased estimator. But it is known that each of the sample mean is a good estimator of the population mean using 10 samples each, but it has been proved that there is no best estimator for the combined 20 samples. Grable and Dill 1959 proposed an estimator that is a weighted average of sample means with weights inversely proportional to the sample variance. This is found to work well, but this is not the uniformly minimum variance unbiased estimator or the best estimator. This is the best estimator till now, till we know what we know till today. So researchers are working on two main lines. One is finding good properties of Grable-Dill estimator, and another is finding estimator that are not uniformly beaten by the Grable-Dill estimator. So in my chapter 1, I found an admissible class of estimators of common mean, and the paper got published from Calcutta Statistical Association Bulletin in 1995. The title was on a class of admissible estimators of common mean of two univariate normal populations. In chapter 2, we introduced two-stage sampling and developed Grable-Dill type estimators of common mean, and it again got published in Calcutta Statistical Association Bulletin in 1998, and the title was Estimating the Common Mean of Two Univariate Normal Population Using Two-Stage Sampling. In chapter 3, I introduced covariates in the model and developed various types of estimators of the common mean. And estimating the variance components and the common mean of normal population in presence of covariates was presented in conference at Calcutta University in 1999. In chapter 4, we introduced cost constraint in the model and developed optimal sampling schemes for estimating the common mean. And the paper Optimal Sampling Scheme for Estimating the Common Mean of a Bivariate Normal Population under Differential Sampling Costs has already appeared in JAS, Journal of Applied Statistical Science. So this is about the work in part 1. I have got 4 chapters, 4 papers. Then in part 2, I worked with estimation of size of a finite population. Finite means it doesn't change under birth or death or immigration. It's finite for some time, so we are looking at that time range at which the population is finite in size, finite and closed. So estimation of size of a finite population, we can see the examples like estimation of total number of fish in a lake, estimation of total number of bugs in a court, estimation of size of wildlife in a sanctuary, or in an urn model approach, estimation of total number of balls in an urn. These all go under estimation of size of a finite population. To illustrate the scenario, let me introduce the urn model approach. So there are 16 balls in the urn. We don't know the number 16, so we would like to know the value of capital N, the population size of the balls in the urn. We use a technique known as capture, mark, release, recapture CMRR scheme. What is capture? We first capture K balls from the urn. So we captured 4 balls from the urn. Then we mark them. That is, we change the color of the ball. So we change the color of the balls from white to black. Then we release them back to the urn. So I have put back the balls in the urn and they get mixed up. Then we recapture a sample, again a sample of size small n. Say among them small m of them are marked. So we recaptured 4 of them again and say 1 is marked. So how do we estimate the population size, that is capital N? We equate population proportion to sample proportion, and if you count here n equal to 16, and if you use the formula k by capital N equal to m by small n, then we get the estimate as k into n by m. So if we put the values k equal to 4, n equal to 4 and m equal to 1, we get n equal to 16, which is a close estimate and unbiased also. But the problem of this approach is that the estimator becomes undefined when m equal to 0, that is number of recaptured marked object turns out to be 0. That can be 0 very well. So in that case, the estimator becomes undefined. Hossain 1995 solved this problem of getting undefined estimate as pick up a ball from the urn, change the color and put it back. Continue the process until a colored ball reappears. If it takes small n steps to stop, then capital N can be estimated by n into n minus 1 by 2. This is a best estimator, unbiased estimator, uniformly minimum variance unbiased estimator. In chapter 5, we enhanced Hossain's estimator and compared it with existing estimators, also studied performance of maximum likelihood estimation of population size. Hossain started taking one by one objects from the population. We started with k objects, k marked objects in the population, and then went on picking up the objects one by one. Later we tried to modify the process where we start with a bunch of marked objects and we go on picking up not one but more than one objects at a time, but the problem become mathematically intractable and we had to avoid it. So the paper on estimation of size of finite population was published from Shankha series B in 1997. For the next chapter, we need to have an idea of Bernoulli sequential estimation. So we have capital N balls in an urn and k of them are marked. So we go on picking up balls one by one. Once we get an unmarked ball, a white ball, we go one step right. If we get a marked ball in the sample, we go one step up. So a sample becomes a path like this. Unmarked ball, marked ball, 2 unmarked ball, 2 marked balls, then 2 unmarked balls. It goes on like this and it can go up to n minus k. So in detail, this is the scenario. We are plotting unmarked balls in the horizontal axis and marked balls in the vertical axis, and a sample looks like a step diagram like this. And Hossain's boundary was this: whenever you get one recapture, stop there. So that is Hossain's boundary. We extended it to m recapture and we call it De and Segupta boundary, and we could improve on the precision of the estimator, but it takes longer time. But after that we thought, why should the boundaries be always straight line? What about a general curve like this? And we studied the property of the estimators under the general curve and got hold of a concept like pushed up boundary, which is pushing the boundary one step ahead in the vertical direction. And we could get the results in chapter 1. That main result proved under an arbitrary boundary of the population size is unbiasedly estimable if and only if the pushed up boundary is closed. This paper was published from Sequential Analysis in 2003 and the title was Bernoulli Sequential Estimation of Size of Finite Population. So these are all my 6 chapters in my thesis. Next, I want to go to part 3, which I had a look after I completed my thesis, and this is pure mathematics known as Ramsey theory. So we start with a simple question: is the following statement true or false? The statement is, given any group of 5 people, there will always be 3 people who know each other or 3 people who do not know each other. The answer is false, because if we take a group like this where 1 and 2 know each other, 2 and 3 know each other, 3 and 4 know each other, 4 and 5 know each other, and 5 and 1 know each other, then there is no triangle. That is, there is no 3 people who know each other. And also there is no 3 people who do not know each other. There is no null triangle. That is also true. So for a group of 5 people, this statement is false. But if we modify the statement as, given any group of 6 people, there will always be 3 people who know each other or 3 people who do not know each other, then it is a true statement and can be mathematically proved. I am avoiding the proof here. In short, we call it Ramsey 3 equal to 6. In general, what is Ramsey MN? We define Ramsey MN as the minimum value of k such that in any group of k people there will always be m people who know each other or n people who do not know each other. Till today, only following Ramsey numbers are known. Ramsey 2n equal to 2, which is trivial. Ramsey 3 equal to 6, which is party problem that I discussed without proof. Ramsey 3 equal to 9, Ramsey 3 equal to 14, Ramsey 3 equal to 18, Ramsey 3 equal to 23, Ramsey 3 equal to 28, Ramsey 3 equal to 36, Ramsey 4 equal to 18, Ramsey 4 equal to 25, proved by Mackay and Radzikowski in 1994. And Ramsey 3, if we define 3 types of relations, whether now we are working with 2 relations, whether they know each other or do not know each other, we can extend it to 3 relations, and then Ramsey 3 equal to 17. Please note that Ramsey 5, the value is still unknown to us. We know that it lies between 43 and 49, but the exact value is unknown. Similarly, Ramsey 6 lies Ramsey 6 lies between 102 and 165, but the exact value is unknown. Maybe we are waiting for the supercomputers to come in. Supercomputers, the quantum computers. We are waiting for the quantum computers to solve the problem. So why is it so difficult to solve Ramsey 5? We know Ramsey 5 lies between 43 and 49. So we only need to analyze 7 cases: 43, 44, 45, 46, 47, 48, 49. But for the case of 43 alone, we need to study roughly 10 power 272 relations where the computers or supercomputers are failing. The above calculations is based on the fact that with n people there are 2 power n into n minus 1 by 2 relations. Let me end with a story from Paul Erdos on best strategy. Suppose one day the demon comes to you and says, give me the value of Ramsey 5 within 24 hours or I shall destroy the creation. The best strategy will be to call up all mathematicians of the world, divide the task and get it solved within 24 hours and give it to the demon so that he becomes happy. But instead, the story continues, instead of that, the demon says, suppose one day the demon comes to you and says, give me the value of Ramsey 6 within 24 hours or I shall destroy the creation. The best strategy to survive will be to, let's say, attack the demon. Thank you.